Today we're going to take a look at section 1.2, exploration with patterns. Like I mentioned, if you did not get a chance to print this out, please don't try and copy everything down. Otherwise, that's all we're going to get through today is my one page of copying new things down. You don't want to do that. Come back in later, watch this video, go through and just copy all the pieces down then. So just sit and bear with me, pay attention for the first few definitional things until we can get to some problems, okay? So to start with, we need some common vocabulary so that we're all using the same thing. And then that way, when you see this vocabulary used within questions, you know what they're talking about. The first one is the word conjecture. A conjecture is a statement or conclusion that has not been proven. It's one of these, like, it's a really good guess, almost like a hypothesis would be or something like that in science class. It's conjecture. A counterexample, though, is something that proves the conjecture false. Right? You really thought that it worked like this, and in most of the times it does, but this one example blows it all out of the water, and now you're wrong. At least you're wrong about it always being true. There are two types of reasoning. There's inductive reasoning, and there's deductive reasoning. Inductive reasoning is a method of making generalizations based on observations or patterns. Right? So up until Monday this week, it was hot. Every day was hot. I mean, not every day, but recent history, right? It was hot. So if on Tuesday my children all woke up, which they did, and they put on shorts, that was their conjecture. Their conjecture was that on Tuesday morning it was going to be hot because they were making that based on the pattern of what the weather had been recently. Deductive reasoning is the use of mathematical axioms, theorems, definitions, or undefined terms assumed to be true and logic for proof. So we often see this happen when we've got an equation that we're actually given, and we're told it's always going to follow this equation. So you're using something that's concrete, definition for sure kind of thing, and then you're making a guess, although it's going to be an accurate guess, right? Because you have a more concrete basis for making the decision. This section in particular, 1.2, we're going to be working with things called sequences. Sequences are ordered arrangements of numbers, figures, or objects. Sequences start as early as pre-K or before. If you were to go to Walmart today and you were going to buy like a little bitty kid, like workbook, the ones that people use during the summer, my kids use these, for the little bitty ones, right? For my 5-year-old, she was in pre-K last year, she's in kindergarten this year. Undoubtedly somewhere in that book you're going to see red triangle, blue square, red triangle, blue square. What comes next? That's a sequence. Okay? And it's patterns, it's math. It looks like pictures, it's math. We do it with numbers, and we're specifically going to take some looks at numbers in this particular class today of how we sort of look at those and figure out what comes next. A recursive formula is a formula based on a pattern established. So when I said, I don't even know what I used. Did I use red triangle, blue square, blue circle? What did I say? Red triangle, blue circle. So when I said red triangle, blue circle, you were using recursive thinking, right, of what comes next. It was recursive. It's the idea, in that case there wasn't a formula, but it's the idea of looking at the pattern to figure out what happens next. That's a recursive idea. A general idea, a given rule, how to get from one term to the next. The other option, especially when we are dealing with numbers and we're comparing recursive versus nth or general terms, is that we're actually given a formula to find the nth term in a sequence. I don't need to know what terms 1 through 10 are. I can find term 11 because I have a formula that tells me how to get there. So I don't care what 1 through 10 are. But without the formula, if I'm basing on patterns, I might need to know all the terms 1 through 10 before I can figure out term 11. All right. Specifically, we're going to look at arithmetic and geometric sequences today. The first one is arithmetic. An arithmetic sequence is a sequence in which successive term is obtained from the previous term by the addition of a fixed number. So let me show you an example of this. If you have 2, 6, 10, 14, and it does dots right there at the end. This would be a recursive sequence, or that would be an arithmetic sequence. If you're looking at it from a recursive way, you can see how you get from one term to the next. What do you do to move between these terms? You add 4. And because it's addition, that's what makes it arithmetic. Now, it doesn't have to be addition of positive numbers. It doesn't have to be addition of whole numbers. It could be addition of half, 1/2 every time. It could also be the addition of a negative, so that it looks like you're subtracting 1 every time or subtracting 5 every time. So I'm adding 4 every time, but I could be subtracting and it would be okay. It would still work because you're adding a negative. This fixed number that you add every time is called the common difference. So the common difference doesn't have to be positive. It could be negative. It could be that I'm adding a -3 every time. So on this one, my common difference is 4. Here, this example, my common difference was 4. A positive 4 specifically, but 4 will work. So it's all about adding, or potentially what maybe looks like subtraction of the same constant value every single time. Of course, our 4 basic operations say, well, if I can do something with addition, I can probably do something with multiplication, and if I do, I'm going to get what's called a geometric sequence. So a geometric sequence is a sequence in which each successive term is obtained from the previous term by the multiplication of a fixed number. And again, we don't have to be multiplying by positives. We could be multiplying by negatives. We don't have to be multiplying by whole numbers. We could be multiplying by fractions. Okay, so we could be multiplying by 1/2 every time, which looks suspiciously like I'm dividing by 2. So let me give you an example. 108, 36, 12, 4. Now these numbers are getting smaller, so it probably feels to you like that we are not multiplying, but we are dividing. So let's just pause for a moment and pretend. If I ask you, what would I have to divide by each time to get the next term? What would you say? It's not negative because the signs aren't changing. Yeah, it looks like I'm dividing by 3 every time. Agreed? So that's what it looks like. It looks like I'm dividing by 3. How can I write division by 3 as a multiplication problem, though? Still not negative. There's no negatives going on. Yeah. It's what is it? The reciprocal is right. Yeah, it's actually 1/3. If you multiply by 1/3, it has the same effect as dividing by 3. So on this one, it's a multiplication of 1/3. Let me show you here in just a second, Valerie, what happens and it looks like when you have a negative involved, though, so you can see how it's different.
Doesn't it keep changing the sign positive to negative?
Exactly. Yeah, you would alternate signs. Yeah. Okay, so you're good. Yeah. Okay, this number that I multiply by every time, whether it's a positive number, a negative number, fraction, whatever we get, that's called the common ratio. It's the fixed number used to multiply to get successive terms in a geometric sequence. Common ratio. There's one more sequence that I would be remiss if I didn't mention. We won't do a whole lot with it, but it's an interesting sequence that you should at least be aware of. Fibonacci is a sequence that comes about in nature. It's where it actually shows up. You see it in rings of trees and in shells and things like this. It's really cool. It's not arithmetic. It's not geometric. It follows a different pattern that's common in nature. And I'd like to show you the first few terms in the pattern so that you can see that not all patterns have to be addition and subtraction or multiplication, division, for a pattern to exist. So take a moment as you jot these numbers down and see if you can figure out how do we figure out what the next term is. What's the pattern? don't spoil it for anybody. Sorry, hopefully nobody will hurt you. Don't spoil it real quick. Just let everybody have a chance to think in case you haven't seen it before. Okay, Emily, you wanted to tell me what you thought it was.
34.
Okay, how did you get 34? You're right.
That is 13 plus 21.
Okay.
1 plus 1 makes 2, 1 plus 2 makes 3, 2 plus 3 is 5.
So the subsequent term is determined by the addition of the two previous terms. So 5 plus 8 is actually 13. So if I wanted to get the next term, 34 is what she said it was, and she's right. She added together the 13 and the 21 to get 34. Okay, it is addition, but it's not adding a constant term every time, so that's why it's not arithmetic. It's going to feel a little bit funny to introduce this definition here in the middle of it because it's like we were just talking about sequences and now you're talking about exponents, but I promise I'll show you where it comes into play real quick. The definition of an exponent, a to the n, if n is a natural number, then a to the n is a times a times a, all that, right? N times. If n is equal to 0 and a is not, then we say that a to the n, or likewise a to the 0, is 1. And we'll justify why that works when we get to chapter 3. For now, just go with it. Okay, a to the 0 is 1. All right, so let's actually see these arithmetic and geometric sequences put into action and figure out what we're going to do with them. All right, so here's our example. We're going to list the next 3 terms. We're going to decide if it's arithmetic, geometric, or neither. Both those things are things we've kind of already talked about. Part 3, or triple I, or whatever here, we have not talked about at all. We're going to find the general equation or pattern or formula or whatever you want to call it. Sometimes it's called the nth term for the sequence. And we are going to answer the question about inductive versus deductive reasoning. So for starters, we have on part A 4 numbers given. What would the next 3 numbers be?
13.
Okay, and how did you get between those?
Patterns adding 3.
Patterns adding 3. Did everybody see that? So perhaps some point somebody asked you, well, what's the common difference? Well, it's 3. Right? We didn't ask there here, but we could answer that. Because we're adding every time, what type of a sequence is this? It's arithmetic or arithmetic. Yep. Either way. Yeah. Okay, so even if you get stuck on part 3 here, you should be able to do parts 1 and 2 pretty quick. Part 3 is a little different, and again, like I said, we haven't talked about it, but I'd like to show you how we go about finding, whoops, it's terrible, how we go about finding the general term. Let me just first say that your book talks about a formula. I am pretty strongly opposed to just giving you formulas and telling you to use them. I'd much rather you be able to create something because you understand where all the numbers came from. So that's how I teach this part of it. If it baffles you beyond all, there is another option in your book. I'm not going to penalize you if you use it, but please understand why it works if you can, okay? Don't just use things because somebody gave them to you on a platter, all right? So what's the deal here? Well, if I am repeatedly adding 3 every time, kind of like this problem on the board behind me where we were repeatedly adding 2 to get the next term every time, right? Or when we got down to the 1002 and 1002 and 1002, at some point in our last lessons, I talked about the fact that repeated addition is the same thing as multiplication, and multiplication is so much easier than repeatedly adding something, especially if you have to do it a bunch of times, right? And in particular, the number that we're adding on this problem is 3. Lots and lots of multiplying, or adding 3. 3, 3, 3, 3, 3. But adding 3 is the same as multiplying a bunch of times, is the same as multiplying by 3. And I don't know how many times I'm going to do it, so I'm just going to say n. N represents a random number of times. Did I do it 1 time? Did I do it 5 times? Well, it depends on where I am in the sequence, right? Yeah, so N is just representing how many times I've added 3. So if I start at the beginning of this, and N is 0, hence I haven't added anything yet, and I plugged in N equal to 0 into this, I'd get 3 times 0, and that's 0, but my first term, it isn't 0. Agreed?
Mm-hmm.
What's the first term?
1.
It's 1. So all I have to do to fix the equation now to do what I want is to simply put a plus 1 on the end. So come out here now. Instead of 3 times 0, I have 3 times 0 plus 1, and what's my first term? 1. Now check it, right? What if N is equal to 1? I'm sorry, I should have plugged in 1 to start with. My bad. That's what happens when you don't watch your notes. N is 1 is what I meant to do. Back up, back up, back up. Erase, erase, erase. N is equal to 1. 3 times 1 would be 3, which is not the number at the beginning, 1. I'm sorry. Okay, so if I run my first term, not my 0 term, my first term in my sequence should be the number 1, and it isn't. Right now it's the number 3. Yes?
Mm-hmm.
But I want it to be the number 1. So what would I have to add or subtract to actually make that happen? 2. And I need to subtract it, right? So if I were to go into this and I were to say, okay, well, I'm just subtracting 2 then from it, right? And maybe I should do it this way. I've never done this, but maybe I should. Your multiplication tables for 3s is 3, 6, 9, 12, so forth, right? Do you see how those lists compare? Whoops.
It's just minus 2.
It's just minus 2 from that multiplication of 3's list. So my multiples of 3's list, it is multiples of 3, but it's just subtracting 2 after I do so. And that's why that 2 is coming out on the end right here as negative 2. We're subtracting 2. And if you aren't sure, you could always check, right? You could plug in the number 2 and see that it works if you didn't want to write out my list like I just did a minute ago. 3 times 2 is 6, minus 2 would be 4. And that is the second number in my list. So the general term, the nth term, is 3n minus 2. 3n minus 2. How about B? Do you see a pattern? Yeah, it's multiplication by 2. So our first question that we're supposed to answer is what are our next 3 terms? So what's after 24? 48. 96. 192. Fabulous. Is it arithmetic or geometric? Geometric, because I'm multiplying. All right. But it's not going to have the same form as the last one because I'm not adding the same number every time. I'm multiplying by the same number every time. So think with me to what happened in about probably 6th or 7th grade, and somebody said, okay, but if I multiply 3 times 3 times 3 times 3 times 3 times 3 5 times, or whatever it is, I don't care what you want it to call, but a bunch of times, there's a shortcut way of writing 3 times 3 times 3 times 3 times 3 5 times. And that shortcut way uses exponents, which is why we talked about it over here. It uses exponents. Everybody good? So that's why we've got these exponents showing up. Now, in particular, the exponent base, the number that's being multiplied, is going to be the number that's being multiplied in your sequence. So on this one, you guys told me that was a 2, right? We multiply by 2 times 2 times 2 every single time to get to the next term. So we have a bunch of multiplications by 2. So here's kind of a little bit of a trick. I'll explain it, why I'm doing it. For a moment, put that up there. Okay? If I put an exponent of n minus 1 and I plug in n equal to 1, what will my exponent now be? 0. And what is 2 to the 0 power? 1. Okay, so I'm resetting it back to 1. No matter what that base is, it's a 2, it's a 7, it's a 52 over 695, I don't care. Anytime I raise it to the 0 power, I get 1. So I'm resetting the number to 1 by creating the exponent to be n minus 1. And then the way that I get the first term, so like how do I get it to start? How do I make sure it starts in the right place? Like on the last problem that I made sure it started in the right place, I had to figure out to add the 2 at the end, or subtract the 2 at the end, right? And I compared things. Well, on this one, it's simpler than that. It simply starts out as the first term in your sequence. So in ours, it's 3. Okay, so let me show you how you can check. If I put in n equal to 1, the 1 minus 1 gives me a 0 power on the exponent, right? Which makes the 2 to the 0, 1. And then the 3 at the beginning makes that whole thing 3. And it's always a good idea to make sure that that didn't just work for one term. Because it could have. I mean, you could have made a couple of mistakes and get it to work out for their first term. So we'll try the second one. If I do 3 times 2 to the 2 minus 1. Start at the exponent. What's 2 minus 1? 1. What's 2 raised to the power 1? 2. And then what's 2 times the 3 at the beginning? 6. Is that my second term? It is.
For the top with the n equals 1, is it equals 2 or equals 3?
Say that again.
For the one underneath the first problem, it says n equals 1, 2, or 3 parentheses 2, 1 minus 1. Would it equal 3 or would it equal 2?
Oh, it's just type. You're saying here. Is that what you're saying? Yes, it should say 3. I'm sorry. Thank you for fixing that for me. You're right. It should be 3. That should have said 3.
I was confused because you said it.
Sorry, and I've got things crammed in here because I'm not spacing things out very well today. Yes, it should be a 3. The 3 at the beginning multiplied by the 1, so we have a 3. Yes. Inductive or deductive reasoning. So let me flip back over to my screen because I know I told some of you guys, don't write this all out. This is too much to write. Here were the definitions. Inductive reasoning is a method of making generalizations based on observations or patterns. Deductive reasoning is the use of mathematical axioms, theorems, definitions, or undefined terms assumed to be true and logic for proof. Which of those types of reasoning do we see happening on our problems right here? It is inductive. We are making a generalization, making a conjecture or a claim based upon a pattern. We might be right, we might be wrong. So let's take a look at another one. And we're going to take a look at, there's 2 parts to this one instead of 3. Here they give us the nth term, right? The last time we created them. Here it's given to us. They want us to find the first 5 terms and then identify if it's arithmetic or geometric. So when I find the 5 terms, it's kind of like what I was doing over here when I was checking to see if my nth term business was right, if I figured it out right. I'm plugging in the number n equal to 1, n equal to 2, all the way up to n equal to 5. So if I plug in n equal to 1, it means I'm going to get 5 times 1 plus 6. What do I get? I get 11. What about n equal to 2?
16.
Yep, it's 16. How about n equal to 3? N equal to 4. I've written that 2 again. Why did I do that? 3, 4. 26. And then the last one, n equal to 5. 31. You are adding 5. You're right. So my sequence is 11, 16, 21, 26, 31. So this is sort of like 1i, double I. Is it arithmetic or geometric? Arithmetic. Because you're adding 5 every time. Does it make sense for everybody? Okay, we're going to do the same thing now with n squared minus 1. n equal to 1, all the way up to 5. All right, so if n is equal to 1, I have 1 squared minus 1, which gives me 0. Then I have 2 squared minus 1, which gives me 3 squared minus 1. 4 squared minus 1. Good. And 5 squared minus 1. So on part I, my pattern is 0, 3, 8, 15, 24. Is it arithmetic, geometric, or neither? It's neither. I'm not adding a constant term every time, right? No, because 0 to 3 would be adding 3, but 3 to 8 would be adding 5. I'm not multiplying by a constant term every time because the 0 in the list is just totally shoots that out of the water. I can't multiply 0 by anything and get anything else but 0. So this one's neither. It doesn't mean there's not a pattern. There is, in fact, a pattern. In fact, take a look real quick. If you tried to say that it was subtraction, 0, 3, 8, 15, 24. Take a look. This is plus 3, and this is plus 5, and this is plus 7, and this is plus 9. Do you see a pattern? Could you find me the next term without the equation? You should be able to. There is definitely a pattern there. Yeah, it'd be plus 9, and then I do plus 11, and then I do plus 13, right? But it's not one of the patterns that we've already talked about. It's a different one. Are these questions inductive or deductive reasoning? They're deductive reasoning. I've got an equation that I'm starting with, or a formula that I'm starting with, or I mean, it's not an equation, it's a formula that I'm starting with, and I'm trying to figure out what happens next based on the formula. All right, so I'm actually going to stop here today because the video that I just posted will start up with example 3 for you to watch over the weekend.